Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at the lab exercise Modelling Precambrian Surface Conditions. So once the Earth's surface had cooled to the point where it could form a solid and stable crust, we know the atmosphere will have begun to exert its influence upon surface processes. And this is going to happen in a few ways. So we know relatively early in Earth history, we began seeing water vapor building up in the atmosphere. This will have led to rain, and it will have led to the buildup of small bodies of water on the surface of the Earth. We know as well that the buildup of these bodies of water will have obviously had some repercussions with respect to things like erosion. And of course, water is a very important part of plate tectonics as well. So this evolution of the Earth's atmosphere is going to have a significant and direct effect on the Earth's surface. Now, we know that the Earth's early atmosphere will have primarily formed through the degassing of the Earth's interior via volcanoes. Now, when we go and look at modern volcanoes and we measure the gases that leave them, we know that they are typically very rich in carbon dioxide, sulfur dioxide, and there's normally a lot of water vapor as well. Now, you're probably thinking, hold on a minute, this doesn't sound like the kind of atmosphere we have now. You're obviously asking yourself, where's the nitrogen? So initially, nitrogen levels would have been relatively low. Now, nitrogen does make up a part of the volcanic gases. However, it's not a major constituent. But nitrogen is a relatively inert gas. So over time, the amount of nitrogen is just going to keep building up and up and up in the atmosphere until you get to present day levels. So the buildup of nitrogen is a steady process that's been taking place throughout geologic history. Now, the early atmosphere will have undergone compositional changes with levels of water and sulfur dioxide decreasing over time and levels of methane and nitrogen increasing. So we've already discussed why the amount of nitrogen goes up. Now, when we look at zircons, which date to 4.4 billion years old, some of them show indications that they have interacted with liquid water. And this would have been the kind of liquid water that was present on the surface of the Earth or in the shallow subsurface. So we're not talking about the kind of water which is coming from the cooling of igneous systems, for instance. We're talking about water which is giving us chemical indicators that it was either on the surface or just below the Earth's surface. So we know that these zircons have interacted with these surface waters, and of course this tells us that around 4.4 billion years ago there must have been bodies of water on the surface, but they were probably very small, and they were also probably transient as well. They probably didn't persist for extended periods. Now, we know by about 3.8 billion years ago that we had substantial quantities of water built up on the Earth's surface. And we know this from the Ishiwa Greenstone Belt in Canada, which dates to 3.8 billion years ago. And as part of that greenstone belt, we can see pillowed basalts, which is a very distinctive texture which forms when basalts are erupted onto the seafloor. So obviously the mafic lava comes in contact with the cold seawater, producing these pillow shapes. So obviously the presence of seawater is essential in order to form that texture. So we know that the Earth's early atmosphere will have been very, very rich in water vapor. However, over time, a lot of that water vapor will have been stripped out of the atmosphere and it will have been converted into liquid water located on the Earth's surface. Now, in the case of sulfur dioxide, that's going to steadily be reduced over time due to its interaction with ultraviolet radiation. So it's steadily going to be destroyed. There's nothing particularly special about that. Now, methane concentrations will have steadily increased over time, and this is due to the reaction between carbon-bearing molecules, so that we're talking carbon dioxide and carbon monoxide, and hydrogen. Now, you're probably thinking to yourself, hold on a minute, hydrogen is not a particularly common element in the Earth's atmosphere. It makes up only a tiny fraction of it. the Earth has insufficient gravity to retain it in the atmosphere, and so a lot of the hydrogen that does manage to exit the Earth's interior is just lost to space. So we don't really hold it for very long. What you have to remember is that in the early stages of the Earth's evolution, its interior will have been more hydrogen rich. So this would have mean these earlier volcanic eruptions will have been pushing out hydrogen in larger amounts versus present day volcanic gases. And so this would have meant that there would have been more hydrogen available in the Earth's early atmosphere to react with molecules like carbon dioxide and carbon monoxide. And obviously that then resulted in the formation of methane. So we know that the Earth's early atmosphere was therefore very rich in carbon dioxide. We know it was steadily getting richer in methane. And we also know that it contained significant amounts of water vapor, although this was also steadily reducing over time. And all three of those chemicals are greenhouse gases. And so this is obviously going to affect the greenhouse effect that the Earth had during that time period. So just to give you some ideas, the amount of carbon dioxide compared to modern levels in the Archean atmosphere was probably somewhere between 10 and 2,500 times greater than present day. And with respect to methane, modelling suggests that the methane concentration was somewhere between 1,000 or 100,000 times higher than present. And once again, these gases are greenhouse gases, and so they are going to lead to an increased greenhouse effect, and this is obviously going to help to keep the surface of the Earth much warmer compared to modern day conditions. Okay, so this elevated greenhouse effect that was very likely present during the Archean especially may help to explain a bit of an issue that we have with the Earth's early history. Now, we know that juvenile stars tend to have a lower luminosity versus mature stars, and they're typically 20 to 30% less bright than mature stars. So this obviously means planets like Venus and Earth and Mars in the early portions of the early portions of the solar system's history will have been receiving less energy from the sun. And obviously, if those planets are receiving less energy, well, that's going to result in lower surface temperatures, and therefore you would expect any surface water on the Earth to have frozen, leading to massive glaciation. Essentially, the Earth should have become a giant ice cube. However, we know that's not the case. So we have this evidence that clearly shows we had liquid surface water around 4.4 billion years ago from the zircons, and we also have evidence that shows that we had substantial bodies of water by 3.8 billion years ago. So we have all this evidence that's clearly showing us that no, the Earth's surface was not a solid block of ice. And so this brings us on to a geological problem, which is called the faint young sun paradox, which states that we know the early sun will have been less luminous than it is now, and therefore we know the Earth's surface should have been receiving less solar energy, and as such it should have been cold enough to cause the Earth to turn into a giant ice cube. However, we also have evidence that clearly shows that did not happen. So the obvious question is, what stopped it happening? And the only logical answer is that the Earth's early atmosphere had a very strong greenhouse effect, and that managed to compensate for the fact that the Earth was receiving less solar radiation by helping to trap the heat produced by that solar radiation on the Earth's surface, keeping the Earth's surface warmer than it otherwise would have been. Another thing that would have also helped to some degree to keep the Earth's surface a little bit warmer than we probably would have expected is that the Earth's early surface probably had a lower bond albedo versus today. That means it will be slightly darker in color, and so this would also have helped to have retain some of that solar radiation, because if you've ever touched a black car on a hot summer's day, you know that it is going to be extremely hot when compared to a white car on a sunny day. Okay, so what are we going to be doing? Now, in this lab, we are going to be calculating and investigating how changing the parameters for the Earth affect the surface temperature. And the factors we're going to be changing will be the size of the parent star, the distance of the planet to the parent star, the bond albedo of the planet, how light or dark it is, and the intensity of the greenhouse effect that the planet possesses. And so we'll use these 4 variables and we'll put them into a calculator, and it will calculate the surface temperature for those given values. So this is going to allow us to initially do some relatively simple investigations, just trying to look at how strong is the Earth's current greenhouse effect, how much heat does it allow us to retain. And it's also then going to allow us to do some basic modeling for the kind of conditions required to cause runaway glaciations, in this case during the Proterozoic. Okay, so the calculator itself is produced by Indiana State University, and you can use the hyperlink located here to take you straight to the webpage. And the webpage itself looks like this. It's relatively simple. I mean, you can't really get too confused. So once you've landed on this homepage, you will then hit build, and at that point it's then going to allow you to begin to put in your variables. So you can put your mass of your star, your distance between your star and your planet, the bond albedo of your planet, and the greenhouse effect of your planet. So before we get into that, let's just run through our variables in slightly greater detail. So the first variable is the star mass. So the size of our star is going to be important. So smaller stars tend to be duller when compared to larger stars. And so this obviously means that if you want your planet to receive enough solar radiation to keep the surface temperature above freezing, you obviously need to move your planet closer to these smaller, duller stars, whereas these bigger, brighter stars, you need to move your planet further away. So if your star is 0.08 solar masses, so the sun equals 1 solar mass, nuclear fusion will not begin. So we know there's a minimum size required in order for your star to actually be a functioning star. So we know that our value for the mass of our star has to be greater than 0.08 solar masses. And we also know that if our star is greater than 100 solar masses, it will be very, very unstable. And this will lead the star to have a very short and very violent life, which will end in a supernova. So as you can see, the size of your star is going to be important. And for the majority of this lab assignment, we're going to simply be using a star mass of 1, because we're dealing with our sun, which has a solar mass of 1. Okay, so our next variable is distance. Obviously, the closer your planet is to the parent star, the more solar radiation it's going to receive, and therefore the higher the temperature will be. And so we see this, so the side of Mercury that's facing the sun gets extraordinarily hot, whereas a planet like Mars, which is much further away from the sun, receives far less solar radiation and is, comparatively speaking, a lot colder. So that one's not really too surprising. So the third variable we're looking at is bond albedo, and this measures how much solar radiation is reflected back into space by your planet. So it's given as a percentage, so it's between 0 and 100. In terms of the Earth, the bond albedo is 29%. And so this means that 29% of the solar radiation is reflected back into space, with the remainder being retained on, in the Earth's surface and in the atmosphere. And so because 29% of the solar radiation is reflected back into space, the bond albedo is 29. So if your planet is lighter in color, so think of any planet or any satellite in the solar system that's, very, very icy, well, that's going to result in a lighter color. And obviously more solar radiation is therefore going to be reflected back into space. And so it will have a higher bond albedo because the percentage being reflected back into space will be higher. And so the bond albedo number will therefore also be higher. In contrast, if you have quite a dark body, that dark color is obviously going to allow the surface to absorb and retain more heat energy. And so that means that darker objects will tend to, retain that energy more efficiently. That's going to help to increase the surface temperature. So typically the lower the bond albedo, so the darker the color, the more heat will be retained by the surface. So the final variable is going to be the greenhouse effect. And this is a measure of how much heat a planet's atmosphere traps. Now, typically, when you think of the greenhouse effect, you imagine solar radiation coming from the sun, passing through our atmosphere, and you think it's that solar radiation that's getting trapped by the greenhouse effect. It's not. The greenhouse effect is actually produced by solar radiation, solar energy passing through our Earth's atmosphere, hitting the Earth's surface, and heating up the Earth's surface. And then the Earth's surface will then re-radiate that heat back out towards space. However, the greenhouse effect will then reflect some of that energy back onto the Earth's surface. So the stronger your greenhouse effect is, the greater the percentage of this energy that will be reflected back onto the Earth's surface, helping to keep it warm. The weaker your greenhouse effect is, the more of that heat from the Earth's surface or the planet's surface will be lost to space. And so that's why when we compare planets with atmospheres of different thicknesses, they can sometimes have a very serious effect on the surface temperature. Of course, the classic example of this is Venus versus Mars. So Venus has an extremely dense atmosphere, very carbon dioxide rich, and so this means any solar energy that makes it to the surface will be heating up that surface, and then when that energy is trying to be re-radiated back into space, the greenhouse effect is so strong that it says no, most of this heat is staying on the surface, and so steadily over time the surface of Venus gets hotter and hotter and hotter. In the case of Mars, we know that Mars has a very thin atmosphere, and so any solar radiation that makes it to the Martian surface will heat up the surface, and when that heat energy is re-radiated from the surface back towards space, because the atmosphere is so thin and the greenhouse effect is therefore very weak, a lot of that solar energy is lost to space, and as such the surface of Mars is extremely cold. So when we are discussing the greenhouse effect, the Earth's modern greenhouse effect is given a value of 1. So for comparison purposes, the greenhouse effect on Venus has a value of about 200. So that shows you just how much more potent it is when compared to the Earth's greenhouse effect. Okay, so there are also some additional information given in these two tables. The first table lists 5 metals, aluminum, iron, lead, silicon, and titanium, and it gives them melting points in Celsius. Not Fahrenheit, Celsius. And then we also have 2 melting points for rocks. We have dry granite and we have basalt. So the melting point of dry granite and the melting point of basalt is once again given as Celsius. Now you're probably thinking, why am I stipulating dry granite? That's because if your granite contains water, when you try and melt it, it will melt at a much lower temperature than a dry granite. So that's a consideration. But in this instance, we're just focusing on the melting point of dry granite. Okay, so how are we actually going to produce data for this lab exercise? So for part 1, we are going to begin with question 1, and we're going to just simply test the calculator by putting in the current conditions for the planet Earth. Now, if we come over here to the calculator on the right-hand side, you'll notice that in the top right, there is a button marked Summary. So if you hit Summary, it actually brings up a table that just allows you to change all of these values in one location, rather than having to go through each sub-page. You can just put the values in one go and There you are. Okay, so as we can see, the values we'll be using is a star mass of 1, a distance of 1, bond albedo of 29, and a greenhouse effect of 1. Obviously, the star mass is 1 because we're dealing with our sun as it is now. The distance is also 1 because we're dealing with astronomical units, which essentially 1 astronomical unit is the distance from the sun to the Earth. The bond albedo is 29 because that is the bond albedo of our planet, and the greenhouse effect is 1 because that is our greenhouse effect. And so once you input your values into the table, you can hit results, and it's going to give you just a brief description of what the surface would be like, and it's going to give you the temperature in Celsius, and it's going to give you the temperature in Fahrenheit. And you'll notice there are 2 spaces here, so you'll then write the answer for this data in Fahrenheit here and in Celsius here. Now, once you've written that data in there and you're moving on to question 2, just hit the summary button again. That's going to take you back to this table where you can then input the data for your next question. So this is probably actually quite a good place to stop before we get too far into the lab exercise. So please take a minute, get up, have a walk around, get a glass of water, and then please come back for part 2.